instruction for us because the finals week starts on start on Friday. So there are classes that meet on Friday that might actually have a final exam on Friday. Our exam is on next Wednesday, the 17th. Okay, we don't have lecture. No lecture. I still have office hour, but we won't have lecture. Yeah, I well, if you want to make it to my office hour, I'll be in person. Yes. Okay. So let me just point to the calendar just so that we know what we are when our final exam is and what time. Hmm, just to be sure. I know I made that calendar entry already, but we'll double check. Okay. Because the last thing I want is for people not knowing when to show up for the final exam and go like, I did not know, I missed the entire final exam. That would be bad. All right, so that is our final exam for this class. So it is on 17th from 10:15 to 12:15 p.m. Okay, so it's a 2 hour long exam starting 15 minutes before the lecture time. So you might need to adjust your alarm clock just so that you can be here on time because if you miss those 15 minutes it's not good, okay? One, you do not have those 15 minutes, and two, your brain is going to get into panic mode. And when your brain is in panic mode, your lizard brain takes over. Your monkey brain goes like, I am going to go to sleep. So the lizard is going to drive the bus. And you know what's going to happen to the bus when you let the lizard drive the bus. Throwing the monkey under the bus at the same time. Yes. So just arrive a little bit early. I would target getting here by maybe 10:05. Okay. So this way you look at the clock, it's like, oh, okay, I got some spare time. I usually open the classroom a little bit early so people can come in, just kind of sit down, lay out all your good stuff, right? And just go like, okay, I can now just take a rest and be ready for the exam when 10:15 comes. Okay. So now that we have this covered, um, we can now talk about the final exam. Okay, so I'm going to talk about the final exam first, and then we can kind of go back to talk about other stuff if we need to. Is that okay? Unless you guys, if anyone has any burning questions, just go ahead and ask those questions first. So, do we have any questions? Nope. Okay, all right. So, the way I'm going to do the final exam is let me see. I'm trying to find a good way to do it. Mm, I have several ways, in my mind. The first one is simply for me to talk about it. Okay. Well, maybe I'll start out this way, and then, if I need to shift to another method, I can do the shift. All right. So the exam is okay. So the last page of the exam, which is also going to be the same format from your perspective, is to take out that paper clip, keep it on the last page so you don't let it fall, between the cracks. I've lost a lot of paper clips. Not that they're expensive, okay, but it's nice to keep them. So keep the paper clip on the very last page. That's the page where you have the actual C code. And I guarantee the C code does compile, okay, so do not worry about whether the C code is syntactically correct or not. And read the C code first, okay? Make sure you understand all the statements. I cannot explain, each statement, during the final exam. So that means, I can't really answer the question of what are we actually comparing here? Are we comparing the address or are we comparing the value? I cannot answer those questions, okay? So you will have to make sure that you understand the C code that we have been using in this class, okay? Like in this case, okay, why is this function call inside the or statement? Is it even legal? Is it even syntactically correct? Okay, I cannot answer those questions. Okay, you have to understand C or C++, okay, well enough to do that. Or I can answer the question of this is the address of what? Is it the address of the entire array or is it the address of element one of the array? I can answer those questions. Okay, but it helps to kind of glance through the C code first just to know what you're dealing with. Okay, and then you put the C code on one side and then you go back to the actual assembly code and then you start the chore of matching the assembly code to the C code. Okay, all right. And this is where it, okay, the C code is also interleaved with the assembly code. So let me go all the way to the top here. So the top part, or the pretty much for the entire first page, is just instructions, but you still want to read the instructions if I would still advise you to read the instructions. It typically just specifies, what day, what time, how long the exam is, and so on. It also explains, what you need to do. Okay, so in this case, I don't think I'm going to change this. Your job is to identify the bugs, explain what they are, and fix them. Okay, and very specifically, associate, what needs to be done. The first one is identification, what is supposed to be done, and what is actually done instead. So you have to explain to me what is the difference. Use comments to relate the assembly code with the C code. So that means all registers involved with the error, if any, should be tracked and explained up to the point of the correction. So that means, if I'll show you the examples, okay? Explain why the expected code is not done or it is incorrect. Change the code to make it work. So is this part understood? So I don't want just the fix. I want you to explain why it's broken to begin with and the proposed fix. Okay. You don't have to use full sentences or full paragraphs. You don't have to write an English paper. Just use symbols. Okay. The easiest way is to say this is what needs to be done. This is what is done, and this is the correction. Okay. It can be simple. Okay. This part is also important for people who have a tendency of, well, since I don't understand what tech is writing, I'm just going to reinvent the wheel because I know how to do it myself. Do not do that because that would actually get points deducted. Okay, so your job really is to understand the C code the assembly code that I have written and identify the problems. Okay, all right. So to explain, you can use comments to relate a register to concept in the C code as much as possible. Note that all relevant register updates leading to the line that asks for the explanation should also be commented and explained. So there are like usually one or two instructions where I will ask you what ends up in register A after this instruction. Okay, so you have to explain it using this standard. To remove code, which means there's a line of code that does not belong the place where it is, you have to cross it out and explain why the instruction should be crossed out. Okay. To change the code, you can do in-place edit, which means you just kind of cross out and replace it, but then you have to also explain why the change is necessary. Sometimes I would also have missing instructions, in which case you can use the symbol like just this, okay, and then put your extra code between those two lines. All changes to code, removal, change, or insertion must necessitate the explanation of what a register has, what which then necessitates the commenting and the explanation of the chain of instructions leading to either the removed line or the changed line. Note that you may be asked about what is in a specific register after an instruction. The answer should relate as much as possible to the concepts in C or C++. So do we have any questions about the long instructions, which is going to be about the same, if not exactly the same for you? Nope. Okay. All right. So this one starts on line 59. Okay. We start with a no op instruction as if we are running it through River Spider. LDI D with 0. That's just initializing the stack pointer. Decrement the stack pointer. And then we do the LDI dot 6 plus LDDB. And then we do a JMPI to main. And then the halt instruction. I spot a problem already. Hmm? Jumping, say that one more time? this will jump past the halt instruction. That is correct. So the question is, why do you think it is jumping past the halt instruction instead of jumping to the halt instruction? Yep, yep, that is correct. They're both correct. They're both correct, and they would both count as the actual solution. But then you have to kind of shortly explain that, okay, and ask and say that if I keep this 6 here, it is going to jump past the halt instruction. Okay. Yep. You don't need to use the slash. We're not compiling the code. We're not assembling the code. You just kind of write next to it. Yeah. Appropriate or inappropriate? Appropriate. Okay. Because I can think of many examples for inappropriate. I might have to turn off the mic. In fact, yep, it's still going. Okay, that's good. So the appropriate command would simply say, just put a pointer here, point it to the 6, and go like this will return to the instruction past the halt, and then you just cross the 6, turn it into a 5. That's all. Okay, so that's all I'm looking for in this case. Or you can switch between these two instructions. That works too. So if you are switching between those two instructions, the easiest way is simply to put a two-way arrow like this to indicate that you're switching the order of those two lines. I understand what that means, and along with if you use this symbol across these two lines, along with an explanation, you get all the points for that. Are we good so far? All right. So now we move on. Okay, we move on to the node definition. So this is the way your exam would look like too. I'm going to interleave the C code in comments with the assembly code. So this way you don't have to hunt for the C code and try to match yourself with, okay, exactly where is the program at this point. Okay, so I hope that helps a little bit. All right, so now we are defining the node structure. Payload getting an offset of 0 is correct because it is the first member. P next is the next definition, and having node underscore payload 1 plus is correct because this one here is accounting for the size of the void pointer. All pointers only use 1 byte, okay, including a void pointer. So this part is correct. Node size is node p next, which is the last member of the entire structure, plus the size of the last member of the structure, because p next is also a pointer, so 1 plus is also correct. So I cannot find anything wrong with the label definition corresponding to the structure definition. Are we doing okay so far? Okay, all right. So then we move on to frame. Okay, frame in this case is its own structure. So frame p node is the first member. It has an offset of 0 from the beginning of the structure. That's good. And then we have pref frame, previous frame, being the second member of the structure. So we have the label corresponding to the first member plus the size of the second member of the first member, sorry, of the first member, which is a pointer here. So that is correct as well. Frame size is the size of the entire struct frame. It is the previous frame, which is the last member of the entire structure, plus the size of the last member of the structure. It is a pointer, that's why it's a 1 byte. So I cannot find anything wrong with the frame label either. Are we doing okay so far? All right. So now we have the global variable circle that is initialized. So we have 0, okay, that's what the 0 is. And circle 1, or the address of circle 1, is in this case, okay, so 1 node size times, okay, so this is 1 multiplication plus the offset or the label of circle. So this is correct. Okay, so this is where you might need to study a little bit in terms of parsing, reverse Polish notation. So the way you process reverse Polish notation is if you see a label, or just a constant, you push it on the stack, okay? In the actual expression stack. When you see an operator, which is typically plus, minus, multiply, or divide, okay, then what you do is you pop the previous two items on the stack, perform the operation, and then you push the result of the operation back on the stack. Is that okay? So that means you see the one, you don't do anything, you push it on the expression stack. You see node size, you don't do anything, you push it on the stack. Now we have two items on the stack. You perform the multiplication, 1 times node size is just node size, which is 2. Then you pop 2, your stack becomes empty, and then you push the 2 back on the stack. And then you see circle, which is really just a label designating the location of this byte 0. You push that on the stack again. So now we have two items on the stack one more time. And then you do the plus, which means the plus is applied to circle and the product between 1 and node size. Okay, so do we have any questions about how to parse and process reversed Polish notation? Now, remember, this is open book and open notes. So between now and next Wednesday, you have more than a week to research and find out what instruction of how to process RPN online is the most user-friendly to you, and then practice. Are we good so far? Okay, so if you're kind of new to reverse Polish notation and you look at this and go, I'm not really sure what is going on, use that as an opportunity. Okay, use this week and a half or so, to research and find out what instructions work best for you. Practice a little bit, okay, and so that on next Wednesday you come here and you go like, yep, I can tackle reverse Polish notation now. Are we good with that? Okay, all right. So this one doesn't sound wrong to me. Okay, this is correct. Another byte 0. Okay, so let me use the mouse pointer so it's actually recorded. This 0 is corresponding to this 0 here. So this time I changed the expression just a little bit. Let me see if that is still correct. So we push the circle, we push the 2, we push node size. So we have 3 items on the expression stack. The multiplication is only going to pop these two, perform the multiplication, and then push the product back on the stack. So now we have 2 times node size sitting on the stack, along with circle. The plus is going to take those two items, perform the addition, and then the result of the addition, because it's the last operator, that becomes the actual value that goes into this byte, which is also correct. It is going to be the address of the third item or element 2 of the entire array. So this one is a 0, and the only thing that got changed is the ordering between these two. And since multiplication is commutative, that means the format is different, but we are basically just getting circle in this case. Are we okay so far with how to parse RPN? Yes. Nope. Well, yes. You if you say, this is not incorrect, but it is inconsistent, then it's okay. Because I if you don't say that this is actually okay, but you just don't like you cannot stand inconsistency, then I would assume that you do not understand RPN, and yep, 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 yep. So make it clear if you just want to comment something on something just because tag this is ugly. I guess it works. Okay, you can say that. Okay, you don't get points taken off that way. But if you don't say that and you just simply mark something, I would assume it is a correction to the original code. Is that okay? I just want to make that absolutely clear. All right. So now that looks good. Okay, now we have is loop. Okay, so this is the C code, which is also on the actual page of the C code. So for those of you who want more contextual information, you can always refer to just the C code. If you just kind of like, oh, this is more than sufficient to give me all the context, you don't have to flip back to the actual C code. It is entirely up to you to determine how you want to use the provided pages. So in this case, we have local variables. Okay, so this is a local variable f. local variable f is at an offset of 0 from the frame itself because it's the first local variable. That sounds about right. And then we have the next one, which is fptr. It is the second local variable. So we look at the offset of the first local variable plus the size of the first local variable, which is actually correct in this case. Add those two, and we now have the offset to the second local variable. So are we okay in terms of why this is the actual correct size of f? Because f is not a pointer. F is an actual struct frame. Uh, yep. So that's a typical name. I try to keep exactly the same standardized format of the name. So when I define the offset of a member in the structure, I would use the name of the structure as the prefix, and then the name of the member as the second part of the name. With offsets to local variables and parameters, I would use the function name as the prefix, underscore, and then the name of either the local variable or the parameter as the second part. So all the standardized notation, I would keep all of those in the test. So I would not intentionally use like different labeling schemes because that's I don't want you I'm testing whether you understand the code, not whether you're adaptive to, oh, this is the new way of encrypting C construct into assembly labels. So that is not what I'm testing. All right, so that's good. Okay, what about result? So result is ptr node size plus. We have a problem here because fptr is a pointer. This should be a 1. So we good? Do we have any questions about that? Okay. So this one is supposed to be just 1 because fptr is a pointer. Every pointer only uses 1 byte. We don't know where it is. I mean, this is an uninitialized local variable. So we're gonna put something into it later. Okay. All right. So that is okay. And then LVS is the offset to the last local variable, which is result, plus the size of the last local variable, which is an unsigned 8-bit integer, which is just 1 byte. So this part is correct too. And then P node is LVS 1 plus because this one refers to the return address that is sitting on the stack between the arguments and the local variables. So this one is actually correct. And P node is the first parameter. So that's why it is next to the return address. And then previous frame is the second one, and it is only 1 byte off because p node is a pointer. That's why it only uses 1 byte. So, so one correction here, okay, node size, this one here should be a 1 instead of node size. So that's the correction. All right, so starting on line 111 and line 112, okay? So this is a prime example of if it doesn't look like what the way we do things in the class does not mean it is wrong, okay? So this is where I'm testing whether you actually understand what it is doing as opposed to how it is done, okay? So this is actually correct. There's nothing wrong with this because we're pushing the 0 on the expression stack. We're pushing LVS on the expression stack, and then we do subtraction, which means it ends up as 0 minus the LVS for is loop, which is a negative number. When you add a negative number to the stack pointer, you're basically decreasing the stack pointer. You're allocating for the local variable size, just the same as our usual sequence. Okay, so there's nothing wrong with line 11 and line 112. Okay, correct. Yep, yep. So you got a quarter of a point deducted. So if each correct correction is worth 1 point, then each incorrect correction which means it does not need correction, but you correct it anyway, that's worth negative 1/4 of a point. So it takes four of those to counter 1 point that you get. So I think that's generous. That's fairly generous, okay? Because I have seen people trying to shotgun the whole thing. It's like, I am just going to make some changes on this line. Maybe it's wrong. I've seen people do that. Well, it is RPN, which is the same order of the instruction, which is you push this, and then you pop those, you perform the subtraction, and then you exactly. That's exactly how we make a thinking box on our head. Okay, it is just going like, oh, this is the pattern. This is the pattern. But do you understand the pattern? I don't need to understand the pattern because the pattern just keep repeating itself. I don't need to understand it. That is how we end up with a thinking box. Okay, and I have my own thinking box too. As much as I try to resist it, it's just human nature to be quote unquote energy saving, aka being lazy. Okay, but that's exactly I want to train you guys not to do. Okay, is to question what we are doing when we see the normal sequence. When you see a new sequence, you ask yourselves, is it doing the same thing as what we usually see, or is it actually different? Okay, so that means you have to understand the constructs. Okay, so do not try to answer this exam only on pattern recognition. Whenever you see a pattern that is different, then you ask yourself, okay, is the new pattern doing the same thing as what tech usually use in the class, or is it actually different? Okay, so that is what you need to do. So I'm spilling the secrets to answer the questions already, okay? But that's the whole idea of teaching. I don't teach the class successfully if I don't spill the secrets, okay? There's no reason for me to keep the secrets. Are we good okay so far? Okay? All right. So jot down in your notes, okay, as you study for this class, make sure that you understand every single statement. What does it actually do in the context of the assembly code program? All right, subtract AA, okay? What does it do? You put a zero in register A, it saves 1 byte compared to the LDI approach. And then we do the LDIB with is loop underscore result, which is the offset into register B. We add the stack pointer, which is now pointing to the base of the frame, to the offset from the base of the frame to result as I think, local variable. So now we end up with the address of result in register B. And then I move on to the next C statement. Okay, we missed one thing. What did we miss? LST in parentheses B comma A. So you have to explain that without the ST instruction, we are not storing to the left-hand side. So your explanation is just that, okay? You need ST instruction to store the result to the left-hand side in the C statement. I mean, it doesn't have to be that long, okay? Just capture the meaning. Hmm? You're inserting a line in this case. So you'll be doing an insertion like this. Yep, you can use an arrow, or you can use whatever empty area here is to write the code and the explanation, and then draw a line to where it's supposed to insert here. So as long as I understand what line you want to insert where, and it is correct, and it has an explanation, we're good. Okay? Now, but this is also an explanation of you need to tell me what register B has, and not just that we need an ST instruction. So that means for this one, in order to get full credit for the bug fix, you have to tell me what is in register A, it has 0. What is in register B, it has the address of result. So that means when you encounter this line, you need to comment A equals to 0. When you encounter this line, you have to say B has the offset to result from the base of the frame. When you get to this line, you have to say B has the address of result. Okay, so it sounds like a lot of stuff to write, but it doesn't have to be long because in order to represent, so I'm just using the whiteboard for this purpose. So in order to say A has a 0, that's easy. Okay, you can use double equal because I just need to know what is in register A. So this confirms that A has a value of 0. So you can use double equal here. Or if you use a single equal, I'm not going to take any points off. After line 16, that's the one that is more difficult. So you can say B has essentially the address of result minus the stack pointer. That would be the easiest way to say that it is the offset. Okay, and then on the next line, you just say B is the address of result. I don't need you to give me the full algebraic, derivation. You can just say that, okay, now B has the address of result. So I would need those comments in order to give you full credit for fixing this bug. Is that okay? The question is why? Because I don't want people just to do it by pattern recognition. I need to know that they know why they need that fix. And not just by going like, well, I matched this to the pattern over here, and this is what the pattern suggests, and I think this is missing this instruction. Because guess what? AI can do that better than you do. If it's just pattern recognition, you cannot beat AI for pattern recognition. Period. Huh? To try, yes. Well, I mean, trying is usually the best way to learn something. Okay, you try, you observe the outcome, you explain the outcome, and then you try differently if it's not successful the first time. Trying the same thing over and over again, it is craziness. Yes. All right, so we have a missing instruction here. So now we move on to the next instruction. We have P node, which is the offset over here. Oh. There has to be something between line 119 and 120. What is it? Add A comma D, right? Because otherwise, register A ends up with the offset from the frame, from the base of the frame to P node, and then we go like, oh, let's just go to the offset. No, the offset is useless unless you convert the offset to an address. Does everybody understand the difference between the offset from the base of a frame to something on in the frame, between that and the concept of the address of the same thing? So we good? Okay. So that means you for the second bug, you have to tell me what is the result of this statement, and then you put in an extra instruction in between, which is add A comma D. And then now it is just P node here, which is the right hand side. And now we have the left hand side. So the left hand side is adding the offset from the base of a struct frame to P node as a member to the offset from the base of a frame to local variable f. That actually works, okay, together, because f itself is a structure. Now, if f was a pointer to a structure, this would not work, okay, but because f itself is a structure, this actually works. So when I add the base of the frame to the whole thing, now we end up with the address of the left-hand side. Once again, I'm missing something here. Where's the ST? So the clue is every time you have an assignment statement of any kind, that has to be a store somewhere. Usually it's the last operation because you have to compute the right-hand side, the address of the left-hand side, and store. If it's missing the store, then you know that, okay, it's an assignment, there's no store, something is missing. Okay, so for this one, you actually have to explain the whole thing because now you have to also explain um, by the end of 121 or line 121, register B is the offset from the base of the frame to member P node of local variable f. Okay, You can use the same kind of notation. Obviously, you have to make it a little bit more complicated than just that, but using the same format. Okay. Then you have to also explain that the next instruction, or line 122, is calculating the address. So by the time we get to the missing instruction, then it makes sense to have the st in parentheses b comma a, because we know that a has the right hand side, b has the address of the left hand side. We just need a st instruction to finish the operation. Are we good so far? So my suggestion is, by default, okay, just comment every single line. Instead of encountering a problem and then go back and re-comment some stuff, just comment every single line. It's not going to take you that long, especially if you like shorthands like this. It'll be fine. Okay. All right. Oh, I forgot one thing. My strategy is, when I see something like this, I will automatically go to the end of the function to see it has a matching deallocation and also the correct return code. That would be my strategy. Now, whether you want to do it that way, it's up to you. So I would actually scroll all the way to the end of the function, skipping all of this crazy complexity, and go here and go like, okay, is that correct? Is that deallocating the local variables? Yes. Do I have the correct exit code? Yep. Okay, that retrieves the return address. That deallocates the space used by the return address, and this will continue execution at the caller. Okay, so that's all good. Okay, I would do that match, right away, as soon as I encounter mm, lines 111 and 112. That's when I would match the end. And then, if I were you, I would actually prepare like little templates for myself. Okay, if I see allocation, I should see the allocation. I should always see the return code at the end of a function, and then I would just check them off. Okay, the worst case I can give you is maybe like 3 or 4 functions. So print, the template, okay, 3 or 4 times, and then each one has little checkboxes. So when you see something, you go like, okay, am I checking this? Am I checking this? Am I checking this? Am I checking this? Are we good so far? With a template, it is harder for you to forget. And if you do the structural way, which means look at the beginning, look for the end, you can have a little marker, okay, colored pencil, whatever, and you can just kind of like check out and go like, okay, this part is already done. So by the time you get to the end of the function, you already know that was checked already. You don't have to check it again. Okay, so those are strategies. Okay, it's important to have your own strategy before the exam. And unless you have photographic memory like what we have just talked about here, you can practice again. Okay, use this whole thing and practice your strategy and go like, okay, does that work? Okay. All right, so moving on. So the next statement is this statement here. This is the offset, this is the address, and I'm missing a dereference here. Okay, so between line 125 and line 26, I'm missing a LD A comma A, maybe. Okay, depends on what I end up storing. So I'm also missing a store instruction in the end. So I have to fix that too. But before we go there, we have to ask, what are we doing here? Okay, so register C has preframe p node with a minus. Okay, this is a subtraction. So the question is, what was in register C before this? So the only time we got a register C is over here. It is the negative amount to subtract in order to allocate all the local variables. And we have no use of local variable C after that. So just look in the code here. So that is definitely wrong. And mm, and register B is the address of P node. Okay. Oh, I see how that's supposed to work. Okay. All right. So we are definitely missing a ST instruction here. So you have to fix that. The question is, what do line 26 and line 27 do together? So the last time we update register B is over here. So you have to remember, by the time we are done with line 22, register B has the address of member P node of the structure F as a local variable. Is that okay? Okay. So what is line 126 doing? It is calculating the offset or the relative difference between previous frame, and P node. And then we are adding that offset back to B. So that means by the time we're done with line 127, we are actually calculating, we have the address of member pref frame of local variable F in register B. Okay, I'm going to pause here to see if we are all getting this point. Okay, okay. So in this case, a picture can be helpful. Okay, so the picture is you have F. Okay, so F. Okay, now this is a little bit disorienting. No, actually, this is not disorienting because high memory address always points up. Okay, so this lower block here is F dot. I cannot remember which one is the lower one. It doesn't really matter. Okay, I can switch the order. This code would still work. So let me just kind of go back. So P node is the lower one. Okay, cool. All right, so we get back to this code. So this is P, what again? Node. Okay, so P node is the lower one, and then pref frame not P node and previous frame. That's it. Okay, so this is F dot previous frame. Okay, so that's how memory is laid out. Register B after line 122 points to P node. It points here. This is register B. After line 122, line 126 is calculating pref frame. The label frame underscore pref frame is 1. The label frame underscore P node is 0. 1 minus 0 is 1. So register C has a value of 1. So when you add register C to register B, you essentially change register B to point here. So now register B is the address of member previous frame of local variable F. Is that okay? All right. So you do need, so how do we successfully, deal with this kind of problem? You need to understand the constructs. You just need to understand what the labels are representing, what is the end result of a calculation, and how memory is laid out when you have a structure. Okay, so those are all conceptual things that you have to track. So we do have a missing instruction here, which is a ST instruction, but because you have to explain why ST in parentheses B comma A is going to work, you have to fully explain all of these instructions too. Are we good so far? Okay, all right. So now we have, we want to see if P node is 0 or not, okay? So we have the offset, we have the address, and then we compare the address with itself, okay? We want to see if the address of P node is null or not. Of course it's not null, okay? Because we're not supposed to be comparing the address of P node, we're supposed to be comparing the value of P node. So that means we are missing a LD instruction between line 130 and line 31. We're missing an instruction which is LDAA. The second A needs to be parenthesized. Are we good so far? Okay. So JZI to is loop and if, that is correct. But if I were you, I would also kind of put a little marker here to say this is the last line. I would use the little post-its. Do you guys know, what post-it we are talking about? Those ones that are kind of like just long and you can stick it and then you can easily put it somewhere else. So use those as a bookmark, okay? put it here, okay? And then you go look for the end, okay? Where is end if zero defined? Or is it even defined? I try to use indentation to help you understand the scoping or the blocks of code. So I just scroll down and go like, okay, do we see, end if zero somewhere in here? Yep, we find it. And it seems to be at the right place, so you check off those items. Okay, so for conditional statements, you have a little checklist. For loops, you have a different checklist. All right, so that checks out, and this logic is correct, okay, because if p node is 0, we go to the else case, or the end of the conditional statement in this case. If it is non-zero, then we proceed with whatever is inside the conditional statement. So we have pref frame, and then we have an immediate LDAA instruction. Definitely wrong in many ways, okay, in two ways. One, this is the wrong pref frame label. Look at the prefix. There's a prefix of frame, which means, oh, we are looking at the offset from the beginning of a structure to the member called pref frame, previous frame. But the C code has nothing to do with addressing any members. The C code says I need pref frame as a either parameter or a local variable. So that means frame as a prefix here is incorrect. It has to be is loop as a prefix. Okay, so you have to kind of mention that. Okay, cross out this frame over here and change it to is loop, and then just say that this is a local variable or parameter, not a member. Okay, and then we jump straight to LD instruction, which is also incorrect because pref frame is a local variable or parameter, and that means we need to add AD between line 134 and line 135. Okay, so after that, we have the right-hand side, and then the left-hand side is FPTR, ADBD, correct, and then the ST instruction is correct in this case. Okay, moving on to the loop here. So once again, we have a control structure. So with the control structure, the way I use the labels is structured. This is inside the then branch, and hence the name then 0. So this is a while loop inside the then statement. So that's why we have a nest. Let me put it this way. So the way I define these labels, you can look at this underscore as a slash, as a path. Okay. So the name of the label indicates where we're supposed to find it. Okay. So when I see a loop, okay, in the C code, I would immediately switch back to the structure mode, which is, okay, we have a begin. Do we have a matching end? And when we get to the matching end, do we have an unconditional branch back to the beginning? Those would be the things that I would check structurally. So I would move my little post-it to line 140 to remember this is the line that I'm actually at. And then I will skip forward until I find the end label of the same thing. So that label would be called isLoop then 0 while 0 underscore end. Okay, and it would have the same indentation. So I can see that. I don't see that. Okay, so that means I need to find a place to put it in. Okay, so now you have to find the end. Oh, wait, I do find it. This is the end of the label. Okay, so I did find the end. And this is the unconditional branch back to the beginning. So that means the control structure of the while loop is taken care of. So now we check off those items on the list. Okay, so you might need to bring you multiple templates for conditional statements, multiple templates for while loop, multiple templates for do while loop, but those are the only three control structures that we have worked with in this class. Okay, so either that or you just have some kind of notation to remember to do this yourself. Okay, so however you want to remind yourself is up to you, but I would do it in the structure way. So now I go back to the beginning of the loop and go like, okay, the structure of the loop looks good. So now we have to evaluate the condition. This is a conditional statement or conjunction to stay in the loop. So when you're looking for an excuse to get out of the loop, you're looking for the negation of this or the negation of this part here. So that means if FPTR is false, we want to get out right away without having to ask another question. So we have the offset, we have the address. Register B, not C, is FPTR itself. Do the AND ABB, okay? If it is 0, then we want to go to the end. That's okay. That's all perfectly correct. And then we try to evaluate the other side, which is the not equal to. So that means we look into P node as an offset to the member of where register B is pointing to. So this is why it is important to track the registers, because register B is FPTR at this point. After the add instruction, it becomes the address of member P node of the structure that FPTR is pointing to. I do an LD instruction here. So now register A is the actual value on the left-hand side of the not equal to. And, oh, okay. So there's a mandatory explanation, which means from here, okay, so start mandatory destination register documentation. So that means even if there are no bugs, okay, from lines 145 to lines 152, you have to tell me what is in the register that got changed on each line, and you have to tell me what it has. Is that okay? All right, so the code is correct, okay? Register A is the left-hand side. So now we have a decrement D, which is decreasing the stack pointer, and then we store register C to where the stack pointer is pointing to, which means I'm pushing register C. What is in register C at this point? What was the last time we modified register C? So yes, okay, so it has the address of FPTR. We push the address of FPTR on the stack with these two instructions, okay? And then what do? We load P node of frame to register C, and then we add the stack pointer to register C. Something has got to be wrong in this case. How can I tell something is wrong? Because I'm adding the stack pointer to offset, but the offset belongs to a structure, not a frame. So I know something is wrong. Now, is it wrong one way or the other way? Because there are two ways it can be wrong. So this time I have to be more careful because I have to look back into the C code and ask, what is the C code asking me to do? So the C code means it says I need to look at P node as a either local variable or parameter. So that means I need to adjust this part here. It is not an offset to a member. It is offset to something on the stack in the frame. So the frame part needs to be adjusted to is loop. Okay, the 1 plus is correct. Okay, we need that 1 plus because I just pushed something on the stack. So that means with the correction, then I would end up with register C would become the address of P node, and then register C becomes the actual P node, and then I do the subtraction. The subtraction is being done, um, well, this is register A, this is register C. It doesn't really matter because in this case, the only thing I need is to see whether they are the same or not. Okay, so then I do some weird stuff here. Okay, I just go like, let's go ahead and pop register C back. Okay, in other words, whatever I saved earlier with the push, I am now restoring. So I used register C for the compare, and then I immediately restore that to whatever register C had, which was from here, which is the address of FPTR. Okay, so is that okay? I mean, can we actually do the increment before the JNZ? The answer is absolutely, because increment and decrement do not affect the flag register. I can do all the increment and decrement without changing the flags register. So the JZI is saying that if they are the same, we go to um, begin, okay? which is over here. That is not correct, okay, because we need to actually continue with the execution. Inside, oh, I take it back. This is the wrong label because if they are the same, that means they're not equal to. If they're not equal to, we continue the loop when they are not equal to, which means when they're equal to, what do? Go to the end. Yep. So that's why you need to change this label to end, not to begin. So that will fix that problem. And then we continue with the loop. So this is the loop itself. This is the entire loop. Yep. So that's the entire loop. And then we continue with after the loop. So after the loop, we have this expression as the right-hand side of the assignment statement. So the first part is whether FPTR is not null or not. Okay. So we just do an AND CC. So the question is what is in register C by the time we get to line 172? So that means when we exit the loop, what is in register C? So then we have to go to the beginning and ask, how do we exit the loop? The two ways we can exit the loop is one is over here. So this is the first reason we can exit the loop. Yes. Let me double check. Yep. So this is the first reason that we can exit the loop. So when we exit the loop, what is in register C? Register C has the address of FPTR. Okay, so take note of that. What is the other reason we can exit the loop? This is the other one. After it's fixed, this is the second reason we can exit the loop. So in this case, what is in register C after when we exit the loop? That would be we push and then we pop it back. So register C will still be the address of FPTR. So by the time we get to this statement over here, register C would be the address of FPTR, not the value of FPTR. So that means you have to insert one line between 171 and 172, which is LDCC. Okay, so you turn the address of FPTR into the value of FPTR. Then we can check whether it's 0 or not, and N0 NCC will do it. So if it is 0, that means this statement is false. So that's how we need to go to the else part here to evaluate it. If it is non-zero, then we can go like, okay, the OR is already done because if this side is true, then the whole thing is going to be true. So we go to the OR done label and make sure the OR done label is doing the correct thing. And it is storing register C to result. So the question is, do we want to store that? Yeah, that would work because register C would be the value of FPTR. If FPTR itself is not null, then this is returning quote unquote true. But what is true in C++? Anything that is not null. So if we know that FPTR is not null, and we just put FPTR into result as a Boolean, that works because it's not null, right? So that part actually works. So I have just verified the I have just verified this part here. Okay, this part is now verified for one branch. So now we have to look at the other branch. Okay, this is the other branch, which is really just taking the return value from whatever the recursive call is and put it into the result. So now we have to check the else part, which is starting from on line 176. All right, so we're supposed to push the address of F on the stack. This is the offset. This is the address. We push it on the stack. We good. We get to P node. Okay, 1 plus is necessary because we just pushed something on the stack. This is the address of P node. This is P node itself, which is a pointer to a structure. This is the offset to a member in the struct node. We add that to the address of the structure, and then we do an indirect, which means we get to the actual value of P next. and then we push that on the stack. Okay, that seems okay to me. And then we just jump to is loop. Okay, what are we missing here? Hmm? Nope, it is a member because it is prefixed with the name of the structure. Hmm? Oh, you want to see the C code? Yep, 170-ish. Okay. We're supposed to return the value of member p next of a node, struct node that is pointed to by p node. So this is correct. This is good because when we get to line 182, register b is p node, which is a parameter, and then we add the offset to member p next of a struct node. Now we have the address of member p next of a struct node that is pointed to by p node. So this part is correct. Okay, we push it on the stack, but something is missing before 188. What is missing? We miss out the entire calculation and pushing of the return address. So how do you make sure that you get this one too? Checklist. The checklist will basically say every time we call a function, we push the arguments backwards, which means the last argument is pushed first, and then we push the return address, and then we do the jump, and then when we come back, we deallocate the arguments, make it a checklist. Okay, so you can call it check, check, check. Oh, wait, where's this one? Okay, and also the JMPI instruction should be on the checklist too, because if we miss that one, then the whole thing is like, why are we doing this? So everything that can be put into a checklist because there's a structure to it, make a checklist. That's what I would do, unless you can remember everything. And I miss my own exam sometimes, and this is why I consistently said that I would be a B student in my own class, just because of carelessness, not because I don't understand, just because oh, I forget about this one. All right. So when we come back, we have 2 increment D. That is correct because we have um, yeah, we have the 2 arguments. We have the 2 arguments on the stack. We have to undo those. And then we get to here, and when we put the register C into wherever register B is pointing to, something is not right. What is not right? Because when you come back from a function call, where is the return value? Which register stores the return value of a function? Register A. This is storing register C to whatever register B is pointing to. Register B is fine, but we don't have the return value in register C. So that means somewhere between line 189 and 190, you have to add CPR C comma A. So you have to manually put the return value of the function call into register C so that by the time we get to line 194, this register C has either the non-zero value from the left-hand side of the or the return value of the function on the right-hand side of the or. You cannot, because this register C can also be coming from from the jump to the label or done. So you cannot just do that. The easiest solution is really just to do a CPR between line 190 and line 191 and just do a CPR C comma A, and that would fix the problem. All right, so this is end if matching the end of the if, but since we have that magical checklist, this is already checked. We're good. So we only have to return the value of local variable result. This is the offset. This is the address. This is the value. We put it into register A, which is the correct register to specify the return value. We're good here. This is all checked already. Remember, we checked based on the structure, so that's also done. So now we just move on to main. Okay, so I'm just gonna pause here and see if you guys have any questions. If the question is, am I still recording? The answer is yes. Okay. I can understand that one. Yep, we're still recording. Okay. The question that I have to you is, how are you going to use the recording to help you? Okay. So I'm trying my best, okay, to give you every single tip that I can think of that you can potentially use. Do you have to use the tips? No. You can come up with your own, okay? Because we do things differently, so you can definitely come up with your own. All right, so we're getting main, okay? So we're close to the end. You can see from the little scroll bar here. All right, so we're getting to main. Main has one single local variable, which is x. So it has an offset of 0 from the base of the frame. We're good. LVS is just x, the label x plus 1, which is the size of an unsigned AB integer. We're good. We allocate, and then I look for the deallocation and also the end of the function. It's like, okay, we have the deallocation. That part is good. Wait, this doesn't look good. What is missing? It's missing an increment D. And where should that increment D be? Should it be before line 242 or between 242 and 243? Between. Yep. Because if you do it before, you get to the wrong location to retrieve your return address, and that will just throw the whole thing into it will go to La La Land. Okay. So that's okay. So make sure that you make that correction. Okay. And then we go back to the beginning, and then we go like, okay, what do we need to do here? This is our second argument. Push it on the stack. Okay. Load A with 0, decrement D, stda. Okay. That should push this return address on, not return address. It'll push the 0 on the stack. Now we need to calculate the address of element 1 of the array circle, which is a global. Okay. So the label itself is the address. This multiplication get me the offset in number of bytes to element 1 of the array. I add up those two, and now we have the address of element 1 in register A, so that's good. And then I decide to do LDAA, not good, because the function call says, just give me the address. I don't care what is there. Okay, give me the address. This goes like, no, I would do one extra step here to get the extra credit so that I can give you the value at the address. Wrong. Okay, because the C code says I just need the address. So cross out line 222 and explain why you have to cross it out. Okay, just explain that the parameter or the arguments ask for the address, not the value. Okay, that's all you need to do. We push it on the stack. Okay, decrement D, stda, all good. And then we have the usual code to push the return address on the stack. That's all good. JMPI to isLoop, which is the actual call. All good. And then instead of two increment Ds, I do something different here. Is that okay? Perfectly fine, right? Because I just put 2 into register B and then I add register B, which is 2, to the stack pointer, essentially doing exactly the same thing as 2 increment Ds. So that's all good. Okay, I put the offset of X into register B, calculate the address, store register A, which is the return value of the function call to whatever register B is pointing to, which is the address of X. That's all good. This returns 0. I mean, usually I don't even do that, but it's not wrong. Okay, you stashing a value of 0 into register A before we do the actual return. Okay, and that's it. That's the entire exam. And we did it in 1 hour and 10 minutes. I don't know what to do with the extra 50 minutes. Hmm? Double check your work. Now, when you double check your work, okay, so this is where second guessing becomes a thing, right? Some people would go back to the code and they would second guess and then they would go like, wait, did I do the right correction or not? Okay. So what do you think leads to that doubt? not fully understanding the concepts. Okay, or not having enough comments. Because if you have enough comments and you double check the comments and they're all consistent, that makes it easy for you to double check your work. It's like, does it make sense? Let me go back. Let me go back. Let me go back. If you don't comment the code along the way, then you go like, oh, wait, what is in this register? Then you have to go do the extra work to go even further back to explain what is in the register. So this is why I recommend that you just comment everything. Comment after each line. Use shorthand if you want to. If you don't like this, shorthand, you can do something like this. Okay, you can say big O of dot 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 means the offset of blah 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 from the base of a frame. Okay, invent your own shorthand. Just explain it ahead of time so I know what I'm reading. Okay, so you can come up with ways that can really shorthand the whole thing. Now that you know what you need to document, so you just need to. I would just do this. Okay, if I were you, I would make your own little shorthand table, attach it to the submission of the exam. You don't have to write a single thing. You just go like, "This is my shorthand. Deal with it, tech." You can even write that in your little shorthand explanation. Deal with it, tech. But that makes it easier for you, right? Because the shorthand that you are inventing is your way of documenting things that feels native to you. So use that, okay? And you can print it ahead of time, just staple or put it into the exam submission. Then I'm gonna go like, okay, I understand what you mean by this. I understand what you mean by this. So when I grade it, I know what you mean when you comment your code with minimal syntax. Are we good? So there's a lot of flexibility that you can use to your advantage, okay? And the fact that you can bring in as much as stuff that you can bring on paper, that's also an advantage, okay? So I'm gonna say that you probably don't need a calculator in this exam, but I will still let you guys bring a calculator. It's just kind of like, Dumble's feather. It's like, yeah, I feel better with my calculator. Okay, fine, bring your calculator. All right. So are we doing okay? This is the entire exam. Good. Okay. So how do you study for this class? Yep. Yep. That's one way to do it. It's the explanation that is important. It's the explanation. So all the programs that we have done, and we're going to do one more on Wednesday. So I'll give you another program. I think I did give you something last week. So I'll do that one on Wednesday. It's not going to be that different. Okay. There are only so many things I can do. The address of the pointer thing, pointer to a structure, getting to a member of a structure, pushing something on the stack as a parameter, returning a value, control structures, which is we only limit our control structures to if, do, and do while. There are only three of them. Okay. How do we translate the Boolean operators? Okay, there's logical and, there's logical or, logical not. You still have to remember the JCI versus the JLI thing. One is for signed, the other one is for unsigned. You still have to remember that. You still have to remember what AND AA does. Okay, why do we use it? When do we use it? Um, yeah, so basically, all the tricks that I can throw in here, they are all documented in the sample programs that we have done. And if you want to, you can bring all of those sample programs with you. There's no limitation of what you can bring as long as it is on paper. Just remember, the more you bring in, the harder it is to find something. Okay. All right. So I don't know what else I can nag you with the next 5 minutes. So I'm just gonna let you guys go unless you want to stay and ask questions. We don't have a lab anymore, so we are all done with labs. What do you mean? The sigh. Yep. Well, if you want to see it as a spell book, that's fine with me. I don't. I don't. I don't have anything against